So, today we will start module 7, and in this week the focus will be on using the power series method for solving second order differential equations. So, in this week there will be five lectures. The first one I'll introduce the power series method. I'll use the example of the Legendre differential equation. Then we will solve the Legendre equation using the power series method and look at the properties of what are called Legendre polynomials. After that, I will talk about associated Legendre polynomials and how these are collected to spherical harmonics, okay, and which is a problem that you encounter in quantum chemistry. And then I will take another problem that you encounter in quantum chemistry, which is the quantum harmonic oscillator, and how you use Hermite polynomials to solve this. Okay. And then we will finish with some practice problems. Okay. So this will be the content of module 7. So let us start with the power series method for solving ordinary differential equations. Now what does a power series method do? It gives you the general solution of a homogeneous second order ODE. So, a typical homogeneous second order ODE is written in this form. So, y double prime plus a of x y prime plus b of x y equal to 0. So, the general solution has this form: y is equal to some constant, arbitrary constant, times y1, which is one of the solutions, plus some arbitrary constant times y2. So, this is the general form of the solution, and the power series method will show you how you can get this general solution of a homogeneous second order differential ODE. And I should mention that though we are talking about homogeneous second order ODEs, this method can also be extended to non-homogeneous ODEs and also to higher order ODEs. Okay. But at least as far as this course is concerned, we will look at second order homogeneous ODEs. Okay. So, the example that I will use to illustrate this, okay, this is one example. It is not a you can take many different examples. Okay. So, this is one example that we are using, and this is called the Legendre differential equation. So, this is a differential equation. I will write the differential equation, and we will solve it using the power series method. So, the differential equation is 1 minus x square y double prime minus 2 x y prime plus n, or I will use alpha here instead of n, alpha plus 1 y equal to 0. So, this is the Legendre differential equation, okay, and later on we will be interested in integer values of alpha. Okay, later on we will look at integer values of alpha, but right now this is the form of the Legendre differential equation. Okay. So, I will just mention that alpha being an integer, okay, there are several physical problems. Okay, so this is a form of solution of several physical problems. One of them we will see later on, which is what is called spherical harmonics, okay, which is related to the solution of the rigid rotor in quantum mechanics. So, spherical harmonics, and this is 3D rigid rotor. This is in quantum mechanics. So, the quantum mechanical 3D rigid rotor is what will be solved using this Legendre polynomials. Okay. Also, I should mention that this solution of this Legendre differential equation, which leads to something called Legendre polynomials, these are also very important in general basis expansions of angular functions. And I am just writing this for now. Okay. We will see later on how this is done, but the basic idea is that if you have a system where you have an angular variable, okay, and usually the angular variable has certain range of values, let us say 0 to pi or 0 to 2 pi, okay, then these solutions of the Legendre differential equation, these are very useful to get to as a basis for various problems with angular functions. Okay. So, now what is the method of the power series method? So, what are the steps in the power series method, and keep in mind that we want to solve the Legendre differential equation. So, I will just list the various steps. So, the first step, okay, so I will write the equation again, 1 minus x square equal to 0. Okay. So, the steps are, so the first one is use a trial solution. Okay. So, you try a solution of the form y is equal to sum over n equal to 0 to infinity C n x raised to n. So, C n is a coefficient and you have x to the nth power. So, basically this is called a power series. So, this looks like C 0 plus C 1 x plus C 2 x square plus so on, it goes up to infinity. Okay. So, this is a trial solution, and the basic idea of the method is to use this as a trial solution in the differential equation. Okay. So, if you use this as a trial solution, then you can immediately write y prime is equal to, okay. Now, what you can do is you will have a sum over n equal to 0 to infinity, and then you have to take a derivative, term by term derivative. If you take a derivative, C n is a constant, so C n will be left as it is. Derivative of x raised to n is n times x raised to n minus 1. Okay. Now, when you do this, you will notice that the n equal to 0 term is actually 0. Okay. So, this actually starts from this sum, even though you can write it from 0 to infinity, the n equal to 0 term is 0. So, you can also write this as 1 to infinity C n n x raised to n minus 1. Okay. So, this is the derivative, and then you can write the second derivative similarly, and this will be sum over n equal to 0 to infinity. Now, you have C n n minus 1 x raised to n minus 2. And again, now in this case the n equal to 0 term is 0, n equal to 1 term is also 0. Okay. So, actually you can write this sum as starting from n equal to 2 to infinity. Okay. And if you look at the form of y has this form. Okay. And now, when you take the derivative, obviously the constant term will give you 0 derivative. So, therefore you will not have a constant term. So, the C 0 term, n equal to 0 term will not contribute to the derivative. When you take a second derivative, both the first two terms will actually go out, they will not contribute to the derivative. So, therefore, the derivative contribution start from C 2 onwards. Okay. So, now once you have this trial form, okay, we substitute in the differential equation, and when you substitute this in the differential equation, what will happen is you will have, so I will write each term, I will write this as two terms. So, the 1 minus x square, I will write each of the term multiplies y double prime. So, the first term is just y double prime. So, that I will write as sum over n equal to 0 to infinity C n n minus 1 x raised to n minus 2. The second term is minus x square y double prime. So, now if I multiply this by minus x square, so I have a minus and I have sum over n equal to 0 to infinity. Now, I have C n n minus 1. Now, I have x raised to n. Okay, x square into x raised to n minus 2 is x raised to n. Okay, so, that is what you will get from the first term on the left. The second term, the minus 2 x y, you can see that it gives you minus sum over n equal to 0 to infinity. Now, you have a 2 and you have n x raised to n. Okay, so, that is what you get from this minus 2 x y. Oops. Minus 2 x y prime, minus 2 x y prime gives you that. Okay. Now, the next, so and the last term will give me plus sum over n equal to 0 to infinity alpha plus 1 no, I missed a Cn here. This should be there should be a Cn x raised to n. Okay, and alpha plus 1. Now you just have y is just Cn x raised to n equal to 0. Okay. So, you can verify that these are the terms that you will get when you substitute this form of y in the differential equation. Okay. Now, what can you do with this? So, this is a polynomial in x. So, what you have, this whole left hand side is a polynomial in x and the right hand side is 0. So, if a polynomial in x is 0, then each power of x should go to 0. Okay, so, each power of x on the left hand side should equal 0. So, this I will say is the second step. So, the second step was to substitute. Okay, now, the third step in this method is to set each power of x to 0. Okay. So, for example, if you look at the power of x raised to 0, so it is a polynomial. So, the constant or x raised to 0 term. Okay. So, how can you get an x raised to 0? So, in the first term here, okay, in this term you can get an x raised to 0 if n equal to 2. Okay. So, if n equal to 2, then you will get something that looks like C2, and then you have 2 into 2 minus 1, 2 into 1. So, that is 2. So, you have 2 C2, okay, and then you have x raised to 0. Okay. Then here in this case you will get x raised to power 0 if n equal to 0. So, in the second term, in this term you should have n equal to 0. So, that will give me, so minus C0. Okay. Now, if n equal to 0, then actually n equal to 0, this becomes 0. So, you have into 0. Okay. This will actually not contribute, the contribution will be 0. Similarly, here also you have to have x raised to 0 in the third term. Okay. In the third term, x raised to 0 comes from n equal to 0. Okay. And again that will also contribute 0. So, you will have minus C0 into 0. In the fourth term you will have x raised to 0 contribution from n equal to 0. Okay. So, when n equal to 0, you will have C0 alpha plus 1. So, you have plus C0 alpha plus 1 equal to 0. Okay. So, what we did is we equated the coefficient of x raised to power 0 to 0. It gives you the very nice relation. It gives you C2 equal to minus C0 alpha plus 1 divided by 2. Okay. So, this is a relation between C2 and C0. Okay. Now, next we can set the power of x raised to 1 to 0. So, what is the coefficient of x raised to 1? So, if you want to have x raised to 1, then here n has to be equal to 3. So, you will have a 3 into 2, that is 6 C3, okay, from this term. Here if you have to have x raised to 1, okay, then n has to be equal to 1, but if n equal to 1, then you have n into n minus 1. So, this is the second term. So, the second term will again be 0, okay, and I will not write it this time. In the third term, you can have n equal to 1. Okay. So, if n equal to 1, then you will get minus 2 into 1 into C1. Okay. So, minus 2 C1, and then again in the last term you can have n equal to 1, and in this case you will get plus alpha plus 1 C1. Okay. This is the coefficient of x to the power 1, and this has to be equal to 0. So, what that gives you is that you will get the relation C3 equal to, so now I will write it in this form. I will write it as minus C1 times alpha plus 1 minus 2 divided by 6. So, C3 is related to C1. So, C3 is proportional to C1, C2 was proportional to C0. Okay. Now, you can go on, you can do this, and let me do it right here. Let me now look at the coefficient of x raised to power n, okay, x raised to power n. So, if you have to have a power of x raised to n, then I will show it in green. So, in this term you should have n equal to n plus 2. Okay. So, what you will get, the term that has a power of x raised to n will actually contain c n plus 2 into, now you have n plus 2 into n plus 2 minus 1. So, n plus 2 into n plus 1, this is the coefficient of x to the power n. Okay. The second term will have x to the power n. So, we will have c n n n minus 1. The third term you will have minus 2 n c n, and the fourth term you will have plus alpha alpha plus 1 c n, this equal to 0. Okay. So, this is what you get from the coefficient of x raised to n, and you can rewrite this. Okay. I will let you work it out. So, but I will just write the final result. So, you have c n plus 2 is equal to, okay, and I will write it in minus c n times alpha alpha plus 1 minus n n plus 1 divided by n plus 1 n plus 2. Okay. So, this is what you will get. What you will get is that c n plus 2 is related only to c n. Okay. So, now the fourth step is to analyze. Okay. So, what do we mean by analyze? So, what we notice is that from C0, okay, you can calculate C2. C2 you can express in terms of C0, and C4 can be expressed in terms of C2. So, you can write C4 in terms of C2 using this general relation that we have, and you can write C6 in terms of C4, C4 in terms of C2, C2 in terms of C0. So, and similarly you can go other side. So, you can write C7 in from C5, you can write C5 from C3, you can write C3 from C1. Okay. So, what this means is that these are the even terms, even powers of x, these are odd, these are terms, these are coefficients of odd powers of x. Okay. So, you can write a coefficient of any even power of x in terms of C0. So, basically you can write you can say that all even power coefficients are proportional to C0. Okay. Now, this is again very specific for the Legendre differential equation. It is not generally true. In this particular case, you found that all even power coefficients are proportional to C0, and you also find that you can similarly see that all odd power coefficients are proportional to C1. Okay. So, basically what you can say is that I can write y, okay, I can collect all the even power coefficients, okay, and they will, so what I will get is C0 times sum of even power terms plus C1 times sum of odd power terms. Okay. So, I can write my solution in this form. So, all I did was I took my original trial solution which has this form C n x raised to n. So, what I did is I take this C n x raised to n, and what I see is that all the even terms C0, C2, C4 etc., they are all proportional to C0. So, I collect them together. Similarly, all the odd terms C1, C3 etc., they are proportional to C1. So, I collect those together and I can write it in this form. Okay. Now, this is a very nice form because you can think of these as basis solutions. So, this and this I can think of as basis solutions, and then what you have is you have the form y equal to C0 times y1 plus C2 C1 times y2. So, you are writing a general solution okay, with these two basis solutions, and so C0 and C1 are arbitrary. So this looks like a general solution. Okay. So this is the crux of the power series method, and this is how you find a general solution of a differential equation. Okay. Now what we will do is we will just analyze this a little more. Okay. So in terms of the method, this is how you use the power series method, and C0 and C1 are two arbitrary constants, and essentially you are done. Okay. Now what we will do is we will just look at the properties of these general solutions. Okay. And this is where we will come across something called Legendre polynomials. Okay. In order to motivate them, what I will see is that in this sum of even terms, even power terms and sum of odd power terms, so the number of terms in each sum in general equal to infinity. So in general, this there are infinite many terms in each of these, okay, because the series keeps on going. Okay. Now however, if alpha is an integer, is a, let us say, positive integer. Okay. So if alpha is a positive integer, then we notice that C of alpha plus 2. Okay. So if you look at C of alpha plus 2, so I can write this as minus C alpha times alpha alpha plus 1, and then I had minus n plus 1, which is nothing but alpha alpha plus 1 divided by alpha plus 1 alpha plus 2, and this is equal to 0. Okay, C of alpha plus 2 equal to 0, and what you notice is that let us just go back to our relation. By the way, I did not mention this, but this is called a recursion relation. Okay, so the recursion relation relates Cn to Cn plus 2. There are many other kinds of recursion relation, but this is one form of the recursion relation that you always encounter whenever you are doing the power series method. Okay, so what happens is that when alpha equal to n, when n is equal to alpha, okay, then the numerator goes to 0 in the recursion relation, and so you get 0. And what does this mean? This means that also C of alpha plus 4 equal to C of alpha plus 6 equal to C of alpha plus 8, all of them is equal to 0. Okay. So all those, any term that is of the same parity as alpha, okay, but has a value greater than alpha. So like alpha plus 2, alpha plus 4, alpha plus 6, all of them, all those terms go to 0. So that means if alpha is a positive integer, then one of the two series converges to a polynomial, that means a polynomial of finite degree. And this polynomial of finite degree is referred to as the Legendre polynomial. Okay. So what is the Legendre polynomial? The symbol used is Pn of x. Okay. So Pn is the symbol for the Legendre polynomial. Okay. N is the degree of the polynomial. So that means your Pn Legendre polynomial Pn is a solution of the differential equation 1 minus x square y double prime minus 2x y prime plus n plus 1 y equal to 0. So the solution of this differential equation, okay, so it is one solution. So Legendre polynomial is one solution of above ODE. Okay, so it is one of the solutions. Okay, so the other solution will be an infinite series. Okay, so if you look at your sum of even powers, so you have these two basis solutions, sum of odd powers. Now one of them, if alpha is even, then this term, then the sum of even powers will go to 0 at when n is equal to alpha. if alpha is odd, then the sum of odd power terms will go to 0 beyond some alpha. So one of these will become a polynomial, and that polynomial is called the Legendre polynomial. So what can you say about Legendre polynomial? So I will just mention this. So it is a polynomial of degree n containing only terms that have same parity as n. So what I mean is that it contains only odd or even terms. Okay. So for example, if you have n even, okay, then Pn will have terms that contain x to the power 0, x to the power 2, x power 4 and so on up to x power n. Okay. If n is odd, okay, then the Pn will contain terms that look like will have terms of x power 1, x power 3, x power 5 and so on up to x power n. Okay. So it will be a polynomial that contains only one type of terms. Okay. So in the next class we look at some of the properties of these polynomials. We look at what the forms of these polynomials are, and we will investigate some of their properties. Okay. Thank you.